Today we'll be running through one potential application of the Myriad data reduction framework. We will be attempting to train a machine learning model to detect possible indications of damage in ultrasonic sensor data. So for the application, we've written a simple desktop utility to run everything for us today. And on the lower half of the screen, I have some metrics running so we can have a look at CPU and memory usage, number of threads, that sort of thing as we proceed. So let's have a quick look at the data we'll be using today. So this is essentially a two-dimensional slice of three-dimensional ultrasonic sensor data. This was taken from an immersion tank, and in the upper left corner we can see what appears to be an indication of potential damage within the sample. So the first step in training a model is fairly straightforward. Essentially what you do is compile a set of sample data, and from that sample data you train the model to learn the difference between a damage indication and just noise. So what we do is we have multiple slices of this ultrasonic data, and for each slice we extract smaller regions. In this case we'll be doing 15 by 15 or 30 by 30. And when we extract a region that looks like this, where there's no indication of flaw, that's a negative sample. So there's no indications of flaws within that sample. If we extract a region that seems to have an indication of damage, that's a positive sample. And so we end up with a set of data. Take a look at it like this. So this is a noise sample, and this is a signal sample. And after we've compiled this set of data, we're ready to train a model. For that, we have another desktop application that we've written, and its purpose is simply to train the model for us, save us a little bit of work in that regard. So we'll just add the data folders that contain our samples. And when we train a model, generally speaking, what we like to do is set aside some of the data to test the model. Most of it we'll use for the actual training, say around 75–80%, something like that. But we do like to save some of it for actual testing. In this case, we'll use around 20%. The Myriad framework offers several different options for pre-processing. This is things that are done to the data before the model sees it. And in this case, we're going to try Sobel edge detection, which doesn't actually take any parameters, so we're okay to go there. And Myriad also has several different types of machine learning models that we can train. Today we'll be trying an adaptive SGD, that's stochastic gradient descent. And in this particular case, we're okay with these parameters. I'm just going to bump it up to use 20 different models to evaluate, and we'll use 6 cores as we go through the training process. And so once we've got our training data set up and we've got all the parameters set, we're ready to go. So we just click train. And you can see we actually already have pretty good results. So this is a fairly small data set, so this isn't necessarily indicative of what you get with a complete data set, but it's hopefully illustrative of the general procedure. So after we click the training button, this shows us what our training data set actually looked like. This is a projection of our data where positive samples, those that contain flaws, are shown in red, and negative samples are shown in blue. So we've actually got a pretty good separation between the two. So that's one possible reason for why we were able to get such good results right off the bat. But we can also run a quick test just to see how well it performs in general on a random subset. In this case, we'll just use, say, 100 different test points and see how it does. And again, it does pretty well, actually. So positive samples are in red, so those are samples that should have flaws. Blue samples are those that should not have flaws. And we don't see any in this particular case, but if the model had got any calls wrong, so it made false calls, they would be shown with X's. So a red X would be that it should have been a positive sample but was labeled negative, and a blue X would have been it should have been a negative sample but was labeled positive. But in this particular case, we're actually getting pretty good performance out of this model for this demonstration, so we can go ahead and save this. Okay, so again, just summarizing the traits of the model. So we used Sobel edge detection and an adaptive SGD, and we got pretty good results for that. So for that, we're ready to actually try and test it on some sample data. So if we bring back the desktop tool, so we can remove these files that were showing us what the input data looks like, and we can add, let's start with some data that it should be able to get fairly easily. So we'll start with data that was actually part of its training set. Hopefully it should show that it was able to detect damage in each one of these. So these are our original slices that we took. And let's bring up the log window so we can watch it running. So our desktop application breaks the flaw detection processing into several different stages. On the left-hand side, we start with data ingestion, so this is where files are read. Scale space is a procedure to consider the input data at several different scales. So if you think about it, if we take a look at one of these input files, if my algorithm expected data to be 100 samples by 100 samples and my flaw was, say, 300 by 300 pixels, the damage indicator wouldn't necessarily be able to detect that damage. And so rather than have the flaw detection algorithm attempt to address that scale space issue, we actually present the sample data in several different scales to the algorithm. And we do that essentially by using what's known as Gaussian pyramid processing, where we blur and subsample the data. So we have the data at each step so that the algorithm can consider it at several different scales. The next step in the processing pipeline would be data preprocessing. So this is data processing that is done on the entire data set. And in this particular case, we want to use our Sobel edge detection that we use to train the model. Sliding window is a small subset. So the sliding model is the same size as the model was trained upon. So if we use 15 by 15, for example, then we would use 15 by 15 here for sliding. And in this particular case, we don't need to do any processing, although several options are also available here. Region of interest detection, this is where we actually make the call to our flaw finding algorithm in this demonstration. In this case, we're using the model that we just trained. We can also use an external application if we have some other binary, and we also have convenient support for MATLAB or Python scripts. Reporting, this is where all of the flaw indications are compiled into a list, and not strictly speaking part of the processing pipeline. The results tab is, after we have all of the results from reporting, we compile those per input file. So each one of these input files, if we found flaws in that input file, it will be compiled as a final result here. So each of the stages is its own set of workers within the ACA framework, and we can configure the number of workers in each pool. I'm just going to go ahead and leave the default of 10, but you could use 1 or 2 or 120. It's very flexible in that regard. And the way the processing pipeline works is each of these stages does its work and then sends it to the stage on the right. So, for example, the data ingestion stage reads the data and then sends it to the Gaussian pyramid stage. Gaussian pyramid stage then does its blurring and subsampling to send to data preprocessing if we're doing any, which sends to sliding window, so on and so forth. So we can update the pipeline with our current settings, and you can see that we have our pools configured and ready to go. So we can run it through and see what happens. Okay, so looks like we've completed, and it looks like quite a lot of flaws here, but it's important to remember that two things are happening here. First, we consider the sample at several different scales. So for larger flaws, it's perfectly normal to expect the same flaw to be detected multiple times. And the other thing that's happening is our sliding window settings here are actually overlapping to some extent. So that means that a single flaw seen at a single scale can be seen multiple times. Now that it's complete, we can compile the results. And if we were able to find any damage, they should be highlighted in this display here. So let me bring up the original data. So you can see in this case, for example, the flaw in the 140 slice index was detected twice. And let's bring up 155. And same here. The flaw that we found was found twice with two separate windows. Once again, found twice with two windows. Two windows again. And on the final slice that we're using for our input data, it only found it once. And that's actually not too surprising. This final index of the ultrasonic data is actually fairly noisy. We're not doing any kind of detrending or smoothing or anything in this case. But it was still able to detect what appeared to be a flaw damage or flaw indication. So overall, I'd say that was successful, but of course we'd expect that with its input data that it was trained on. So we can go ahead and remove these, and let's have a look at what happens when we try to examine an entirely new section of data. So this is data that we have not seen before, that our model has not seen before. And so we'll see if we're able to detect any flaws. So here's our sample data. And again, this is data that the model has not seen before. And this is a calibration standard, so it's got several flaws. So you can see that we've got, looks to be about 3 columns and 4 rows of flaws. And since we've already got our processing pipeline configured, we don't actually have to do anything else. We're ready to go. I'll just clear the log window so we can watch the progress. And let me resize that for a minute so we can take a look at the metrics as it runs. Okay, let's resize that. And compile the results. And again, we have the one data set that we tested, so we'll just have one set of results. And here we are. So you can see that this actually shows a couple of different things. So first, it shows that each flaw was detected more than once. It also shows different scales. So larger windows would be one scale, smaller windows would be a different scale. And looking at the results, it's actually not too bad on the first run. Bring up the number of colors, you can get a better look. And so it was able to find quite a lot of the flaws. The larger scales actually found overlapping flaws. So it looks like it's catching these smaller indications in the top left corner as well as the larger ones. And you can see that as the scale changes, it's zeroing in more and more on these deeper flaws. And the reason is because when we change the scale space, we're also blurring in between. So these low-level indications will actually disappear as we reduce the scale and we continue blurring operations. But it was able to detect most of them. There are 3 flaws over here that it was not able to detect. With additional training of the model, with some pre-processing, so detrending some of this background noise, I think we could probably get some better results. We can take a look at some different color scales and see if that will help us to make out the indications a little bit better. And so this is actually a pretty good display. This actually is almost a binary display where the background is essentially reduced to nothing and all we're left with are the possible flaw indications. So this is one potential application of the Myriad data reduction framework. Thank you for watching.